Good afternoon, everybody. My name is Marco Zambianco, and I am a PhD student at Politecnico Milano, which is a university located in Milan, in North Italy. Today, I'm going to present the work Mixed-Numerology Interference-Aware Spectrum Allocation for Enhanced Mobile Broadband and Ultra-Reliable Low-Latency Communication Network Slices. I will first provide an introduction of the problem and the system model, and then I will discuss the employed methodology and the related results. In our work, we consider the multiplexing over a shared radio interface of broadband slices that offer a high data rate communication and low latency slices that are suited for mission-critical application requiring a low communication delay. A major challenge in this context is the design of spectrum allocation techniques that can effectively meet such contrasting service requirements, given that the radio spectrum is a limited resource and over-provisioning is not possible. In addition to this, the employment of mixed numerology access schemes increases the complexity of such spectrum allocation policy due to the fact that, differently from classical orthogonal frequency division multiple access schemes, the subcarrier spacing is heterogeneous. So, on one end, this access technology improves the physical area flexibility to tailor the data transmission according to the user feeding statistic. On the other hand, it introduces interference, since the orthogonality condition between subcarriers is no longer ensured. Following this observation, our contribution in this work is to consider these two problems under a unified framework, and to achieve this objective, we designed a spectrum allocation policy leveraging deep functional learning that maximizes the data rate of each service while satisfying the related service level agreement requirement, and at the same time, it mitigates the internumerology interference suffered by each slice in order to enhance the service provisioning performance. Given this problem, we considered the following system model depicted in this figure. So we considered a radio access network that is shared by a mobile broadband slice and by a low latency slice that will be characterized with different numerologies as shown by the resource block granularity. In particular, we assigned a wider subcarrier spacing to the low latency service, so a higher numerology. Moreover, we considered different traffic statistics. In particular, we considered a full buffer model for the broadband users, whereas we considered a bursty transmission of small packets for the low latency users. In this scenario, the network owner, that is the entity that manages the network resources, allocates the available K bandwidth parts to the users of each slice in order to fulfill the related service requirements. Our goal is indeed to design this allocation algorithm by also accounting for the internumerology interference that arises when the two services are contiguously allocated over the base station spectrum. We formalized this allocation problem by formulating an objective function that allows to maximize the aggregated throughput of the U users over T time slots and K bandwidth parts. In particular, we highlight that the data rate is computed using the classical Shannon formula, where X is the allocated indicator variable, and the function I allows to analytically compute the internumerology interference contribution according to the bandwidth part assignment. For what concerns the problem constraints, we characterize the broadband service with a minimum data rate requirement that has to be provided to each user, whereas we characterize the low latency service as the minimum data rate required to empty the buffer queues of each user before the latency deadline. Finally, we define some feasibility constraints to ensure that the bandwidth part allocation is unique and that the allocator variable X is integer. From this formulation, it is possible to see that the problem is NP-hard and that the solution is the result of a sequential decision-making that maps a suitable number of radio resources to each user over time. For this reason, traditional resolution schemes are computationally inefficient, and so we leverage deep reinforcement learning to design an agent that can approximate the optimal allocation by means of a trial and error process using a model-free approach. So, to apply reinforcement learning in this scenario, we reformulated the problem according to a Markov decision process. So, we define the states as a collection of parameters useful to assess the quality of the current bandwidth part allocation. These parameters are the buffer status of the low latency users, the rate requirements of the broadband users, the channel gain provided by each bandwidth part, and the achieved data rate of every user in the previous time slot. Note that the user data rate information is useful not only because it enforces the Markovian assumption of the model, but also because it indirectly contains the information about the internal interference level. And in this way, the agent can better correlate the obtained reward with the interference dynamic. The action space consists of all the combination of possible bandwidth part allocations that are available for a given number of users. Every action is identified by a multidimensional vector of k elements, where each coordinate corresponds to which users have access to the k bandwidth part in time slot t. So basically, in other words, each coordinate corresponds to a user ID that also identifies the type of service. Finally, the reward function, that is the objective that the agent maximizes during the training phase, is composed by two terms. The first terms correspond to the total data rate computed according to the selected action, whereas the second term enforces probability constraints in the form of a penalty function P that provides a negative reward when the service requirements of each user are not satisfied in the current time slot. So with this reward design, the agent is incentivized to satisfy every user in the least amount of time in order to avoid any penalty. So from this Markovian formulation of the problem, we can observe that the action space increases exponentially with the number of users and bandwidth parts, and this fact can make the agent exploration very inefficient and hinder the policy computation. To overcome this issue, we employed an agent architecture that allows to effectively explore the environment by decomposing the original allocation problem in smaller subproblems that are easier to solve. In this regard, we employed branching Dueling Q-networks that, for those who are familiar with deep Q-learning, this agent can be seen as an extension of Q-learning for multidimensional action spaces. Here in the picture, you see the agent deep neural network that takes as input the environment state previously defined that is propagated throughout the multiple network branches. Each network branch can be considered as a subagent that is in charge of allocating a single bandwidth part to one of the U users. So basically, there are k branches, one for each bandwidth part, and each branch has a number of output neurons equals to the number of users. The agent computes the global bandwidth part allocation by selecting the output neuron from each branch, providing the highest reward in order to retrieve the original action structure that we defined before. Moreover, there is an additional module denoted as a shared state value estimator that computes the expected reward of the agent for being state S and distributes this value across the various branches to promote their cooperation in maximizing the global reward R. Finally, we proposed an additional module that we indicated as action masking module, and its purpose is to improve the learning performance of the agent. As you can see from the figure, the idea is to artificially lower the expected reward of the low latency users having an empty buffer, so they are never scheduled by the agent. The motivation behind this design choice is due to the fact that in the initial phase of the learning, the agent does not know that scheduling empty buffer low latency users is pointless since they have no traffic to transmit, but instead it has to infer this information by correlating a lower reward at every time step. This behavior slows the agent learning effectiveness, so that's why we designed this action masking scheme in order to embed the a priori information on the empty buffer information within the training phase. I will now present the results obtained by the proposed approach. We implemented both the network environment and the agent using MATLAB, and as a main simulation parameters, we considered a radio access network of 10 MHz divided in 6 bandwidth parts. We assigned 15 kHz of subcarrier spacing to the broadband slice and 60 kHz of subcarrier spacing to the low latency slice. As service requirements, we consider that the broadband slice has to provide at least 1.25 megabits per second to each user, whereas the maximum delay of the low latency slice is 4 milliseconds. Moreover, we assess the performance under different network loads reflected by a different number of users. Finally, we compare the agent allocation policy with the one obtained with the round-robin schemes that provides the highest allocation fairness since it equally divides the resources among users, and with the weighted max rate schemes that provides the best route performance since this metric computes the secondary priority of each user according to its buffer occupancy. Of course, these two schemes do not consider the interknowledge interference, so they also allow us to indirectly assess the impact of the interknowledge interference mitigation performed by the agent on the overall performance. We start by discussing the broadband slice performance. In particular, we plot the cumulative distribution of the per-user data rate obtained by the considered schemes when the number of users is 8 and 12. The blue curve is the agent, the red curve is the run-robin scheduler, and the yellow curve is the weighted max rate scheduler. We observe that the agent provides a user data rate that is higher than the one achieved by the weighted max rate scheme, and at the same time, it ensures a violation probability, that is the probability of having a user data rate lower than the minimum required data rate, that is lower than the one obtained with the round-robin scheduler, that is indeed the fairest scheme. Instead, when the number of users is 12, we observe that the agent provides a lower data rate than the one obtained with the weighted max rate scheduler. However, it still ensures a lower violation probability when compared to the other two schemes. So this behavior highlights the agent capability to adapt to different load conditions to ensure the service level agreement fulfillment. Similarly, we plot the service performance of the low latency users in terms of transmission delay, where we dropped packets exceeding the latency deadline. Even in this scenario, the agent outperforms both benchmark schemes by ensuring a lower average delay as well as a lower violation probability. In particular, we highlight that the limited performance degradation of the agent when the number of users is 12 due to the fact that the agent tries to allocate banded parts of the same numerology over contiguous spectrum regions. This has the effect of mitigating the interknowledge interference, which improves the overall service provisioning. Next, we present the aggregate data rate performance of both slices. It is possible to see that the agent achieves a similar performance to the one obtained with the weighted max rate scheduler when the number of users is 8, whereas there is a performance degradation when the number of users is 12. However, this is due to the fact that the agent trades off the optimal cumulative data rate to provide a lower violation probability compared to the other schemes, as I showed you before. So overall, we can say that it performs better from a quality of service point of view. Finally, we show the performance gain in terms of violation probability for both slices when the interknowledge interference is considered. In detail, we compare the performance achieved with the interference-aware agent implementation, the blue curve, and with the interference-agnostic agent implementation, the red curve, that does not account for the interknowledge interference during the training phase. We can observe that the interference-aware agent guarantees a lower violation probability in both network scenarios. So this behavior experimentally quantifies the benefit of interknowledge interference mitigation to boost the system reliability. In conclusion, we proposed a deep reinforcement learning approach to compute an allocation policy that satisfies the service requirements of broadband and low latency services, and that, at the same time, minimizes the interknowledge interference. We adopted an agent architecture based on branching dueling networks that scales efficiently with the number of users and that allows to improve the agent learning performance during the training phase. Finally, although the training phase is time-consuming and it is performed offline, the online deployment of the agent is much more time efficient since the banded part allocation is computed by simply feeding the agent deep neural network with environment states and then taking the maximum value of each atom neuron in each branch. And with this, I have concluded my presentation. Thank you for your attention.